Yeah, I will be talking about AVM, and the scope of this talk will be more modest because I will only focus on the things that we have implemented so far. Great. So today it's Anoma Day, and if you want to write an application in Anoma, you will have to interact with the Anoma Resource Machine. So basically, the Anoma Resource Machine is the part of the Anoma protocol that defines and enforces the rules for valid state updates that satisfy users' preferences. Now, if you try to write an application in the resource machine directly, you will have to learn many new concepts, such as resource logics, nonces, actions, delta proofs, and many new stuff. So yeah, writing an application can feel a bit daunting. In fact, that's a bit how I felt. Like, it's a lot of work, and it's a lot of small details that you need to take into account. But we don't want to be that epic. We want to be something simple. So how did we achieve that? Well, we built an object-oriented programming layer on top of it. And the benefits of this is that, well, object-oriented programming is already familiar to most of us, so it's very easy to pick up. And then you don't need to learn and worry about all the details about the resource machine. In particular, you don't need to write the logic functions. Those are automatically generated for you. And you get some free safety guarantees. And there is a bunch of other stuff that you don't need to care about, like creating nonces, worrying about ephemeral resources, or creating compliance units. The pipeline is very simple. It is like this. You write your programs in the AVM layer, and then the compiler translates them to the resource machine model. It's worth noting that we have made like non-essential simplifications to the resource machine because we didn't want to deal with low-level details such as references or serialization of data. And then for this presentation, I have added an extra layer of pseudocode, which is Java-like syntax, for you to be able to more easily follow the examples. And the AVM examples will be shown in lean code. Great, so this is the first example. Here we have some Java-like code that defines the counter class. This class has a single private field called value, which is a natural number. And then we have one constructor, which sets the value to 0. And we have a method which increments the value by some given amount. I think that's all very clear. So how would we write this in AVM? Well, first we need to define the host struct in the host language, in this case Lean. So that's a very simple struct with a single field called count. Next, we need to define the type signatures for the class and for the members. So for the class, we just give it some name, and we give it the type of the private fields. In this case, a single natural number. Then we define the constructor. The constructor, it's called ini in this example. We have only one constructor, and it takes no arguments, so we just pass it unit. And finally, we have a single method called increment, which takes a natural number as an argument. Okay, so we have the type signatures, and next we have to define the body, the implementation of the class members. So for the constructor, it's very simple. We define a constructor that takes no arguments and returns the counter, that's the struct that we defined earlier, with the count initialized to 0. And for the method, we simply define this method, which in the body we take 2 arguments, the self counter, it's the counter that we are modifying, and the step, which is a natural number. And then we return self with the count updated with plus step. So that's all very simple and straightforward. And then finally, we need to translate between the AVM layer and the host language layer. So we have this generic object definition here, which just has the quantity and the private fields. And in our case, the private fields are just a natural number because we set that in the label. And then we can translate from the counter struct to the object by simply setting the quantity to 1 always and then we set the private fields to the count of the counter. And then in the other direction, we simply check that the quantity is 1, and we create a new counter with the count set to the contents of the object private fields. And that's basically all that we need to do. So what do we get in return? Well, we get a new counter transaction. That's a transaction that creates a counter initialized to 0. This is a transaction in the Anoma Virtual Machine. And we get an increment transaction, which increments the counter. And also, as I mentioned before, we get some safety guarantees. And this is kind of important because this guarantees that the objects that you create through the AVM layer can only be updated through the API that you have defined in the class. So for instance, if we try to subtract from a counter, the resource logic will fail. So yes, moment to celebrate. Thank you. And so what's the overview of the AVM layer? Well, as we have seen, you can define classes, you can define methods for the class, you can define constructors for the class, you can define destructors, which are basically to remove objects or destroy them. And then we have multi-object functions, which we haven't seen yet. And well, a method modifies a single object, the self, but it's usually convenient to be able to modify multiple objects in the same transactions, or to modify an object and create another object. And for this, we have functions. Okay, so now I'll show you an example that involves functions. I don't have time to show you the full code of the example, so I'll just summarize the interface. This example is called Kudos Bank, and it allows the users to first open a bank. So for instance, Jonathan, you can open a bank, and then someone else can come to your bank and create tokens of their own denomination. So for instance, Lukasz could come to your bank and create 10 Lukasz tokens, which will be stored in your bank. Then the owner of these tokens can transfer them to any other user. And the owner can also issue a check. So issuing a check means you subtract, for instance, 5 Lukasz tokens from Jonathan's bank, and then you create an independent check, independent from the bank, but it will still be owned by Lukasz. And then you can fully transfer this check without any bank being involved. And then finally, you can deposit this check in the same bank or into some other bank. Great. So now I'll show you the code for issuing a check. So it looks like this. This is in the Java-like syntax. So we have this function that takes a bank as an argument. That's the object that we'll modify. It takes the denomination of the currency, of the token. It takes the quantity that you want to retrieve, the owner as a public key, and the private key to show that you're really the owner. Great. So first we have some assertions. First we assert that, well, you're really the owner. We check that the amount that you retrieve is at least 1 to avoid having empty checks. And we check that your balance is at least the amount that you want to retrieve. Finally, we modify the bank by subtracting from the owner account, and we create a new check. Okay, so that's in very clear. And next, how we would do that in AVM. So we have this function, which has several parts. The first part is you specify which objects are involved in the function. In this case, it's only the bank. Then we specify the list of checks that we want to perform. These are the same as in the previous slide. So ownership, quantity, and balance. And then in the body, we have two parts, updated and constructed. In the updated part, we have the objects that are modified from the arguments. So in this case, we have the bank here. And the bank, we basically subtract the amount of tokens that you're removing from it. So yeah, very straightforward. And then finally, in the constructed part, we have the new check that we are creating. And we're setting the denomination, the owner, and the quantity. Okay, so any questions about this slide? No? Right. So that's all I have for AVM 0.1. That's the summary. So what we achieved is, well, we have a nice object-oriented layer that abstracts all of the resource machine, difficult details. This resulted in a very dramatic speed up in application development time, which is very nice. You also get strong safety guarantees for free, as I mentioned before, and it's already ready for you to start designing applications in Anoma. Now, the prototype itself is implemented in Lean, but it should be very straightforward to translate it into another language, such as Rust or Elixir. So, what's next? Okay, so that's a summary of the year. Before AVM, there was the dark age, where you had to, well, be an expert in the Anoma resource machine. But since June, we have started to work on AVM 0.1, which we finished in the middle of August. And then we started to work on the next version, AVM 0.2. That will be released later this year. So just a quick comparison between the two versions. Well, the next version will have everything that we currently have, plus some additional features. For instance, we'll be able to have nested objects. So when you define an object, one of the fields can be a reference to another object in the system. You'll be able to call methods from your methods body, which is not possible at the moment. And also in 0.1, every method call or every constructor translates into a single transaction, but this can lead to some inefficiencies, so we will change that in the next version. And a single transaction can have multiple calls. We'll also work on intents, on having a better way to express intents, and we'll also work on having a better surface syntax for it. So that's all I have. If you want to keep updated with the changes, please check out this repository. Everything happens in the open, so I mean you can try it out. If you have problems, you can open an issue, and if you like it, you can drop a star. And just to wrap it up, I'm personally very excited about this project because, well, before when I had to write the normal applications, it would take me a week or two, and I would never get it quite right. But now I can just do it in a couple of hours, which feels great. So yeah, thank you very much for listening, and I'll see you soon. Yeah.
Well, you'll see them right now because they have questions. Thank you, Jan. Any questions? Guests first.
Raise a hand first. Hello, I noticed you said in the AVM 0.2 you were having multi-call transactions. Do you mean that you're compiling these multiple actions, or what exactly do you mean by that?
I mean that you can call multiple methods. Like for instance, I can increment two counters in the same transaction.
Yeah, but like how? like the mechanism.
Well, I mean, we are still developing it, but basically, we have some messages that we send to each of the references, and then you can put that in different actions in the same transaction, and it all works out.
Okay.
But I mean, yeah. The details of how this compilation works are a bit, more complicated. So I think the best way to go about it is by looking at the code.
Okay, thank you.
Yeah, I've got a messy and underinformed guest question. Maybe it helps if we go back to your Kudos Bank example. It's about the resource management. I'd like to understand, like your example there, where you said, like for instance, like creating a check, and then you have this finite quantity, which is the number of those tokens, and I guess all these things live in the resource machine. When you put it into the check, is that just a different wrapper or a different owner around the same underlying resource, or does that create like a new resource in this example?
Yes. Yeah. Right. So a bank is a single resource. I'll start from the beginning and then I'll answer your question. Yeah. Okay. So a bank is a single resource where we store as a hash map, for every customer, how many tokens of each denomination they own. And that's a single resource. Then when we transfer within the same bank, we don't create any new objects. We just change these balances. We move from one entry of the hash map to another entry. Fine. And then when we create a check, we are really creating a new resource. So then we'll have, well, the bank will be modified, and then we'll have a new resource which will contain the information of the check. So that will be the quantity, the denomination, and the owner.
Okay, thanks. That really helps. But then my couple for me, it's about like ensuring that the overall balance here like doesn't leak anywhere, because this is now a new resource that's with these checks. What about this underlying balance that it contains? Is there some constraint there?
You mean for the balance check on the resource
Yeah,
machine?
because like let's say it's taking 5 away from the bank, and now it contains 5. Is this 5 here, that unit there, tracked is anywhere as being constrained?
So this balance has to be checked on the application level.
Okay.
The Anoma Resource Machine doesn't do that.
Right.
And yeah, you just...
so it's the applications layer's responsibility to ensure that this is a conserved quantity. It's not part of the resource machine here for the example of the balance.
Correct. But because you write, so... no, I should go forward. So you'll write this kind of code eventually. And here you can see that the amount that you're subtracting coincides exactly with the amount that you have in the check. And because this is in the code, the resource logics that we define automatically in the AVM layer already check this. So in this case, you will not have to write any extra code for this to be satisfied.
Got it, thanks.
Any other questions?
So my question is regarding what is the audience for this AVM? And yeah, that's my first question.
So this is a research project. The goal of this project is to see how much we can simplify the process of writing Anoma applications by providing this object-oriented layer. And if this later matures into a real language and a real compiler, then this is great. But for now, it's that.
Like, I'm curious because, I mean, you developed this in Lean, and I was, well, intrigued about the features that you actually use from Lean to develop this. And which is connected to my third question was, like, why not to use... If this is intended to the user, to the final user, why not to pick like object-oriented programming like Python or something like that, so you can compile down to the, how you call it, AVM?
Resource machine model?
Yeah, ARM.
Yeah.
Low syntax, yeah.
So we did this in Lean because this is meant to be a prototype, and like in Lean you can type many things, like you can type many of the assumptions that you make in the model, which really helps us be a lot more confident about the prototype that we're writing. That's basically the main reason. And we don't really care whether the object has objects or as first, class elements in it, because we don't really use them. I mean, Lean doesn't have them, and we don't need them. But then now we have the prototype with all the, all the compilation steps, like really spelled out and type checked. And then if we simply want to translate this into Elixir, which will probably happen at some point, then you just look at this as a reference, as a specification, and then you basically translate it into whatever language you choose. I think it really helps.
And why not to pick another object-oriented programming?
Because they don't usually have the rich type system that Lean has.
No, but once you figure out everything,
okay.
I guess you can inform that in kind of report or whatever, and somebody else can just make the front end for that, the back end for that language, maybe.
Yeah. I think that's an option, yeah.
Okay.
Any other questions? All right, let's give it up again for Jan.